Welcome everyone. Today we're going to talk about projectile motion. We're going to learn about what happens when you launch projectiles either horizontally or at an angle. We're going to learn how we can separate the vertical and the horizontal motion. So first, projectile motion. Projectile motion is when you have an object that is given an initial velocity in the horizontal direction, sometimes also in the vertical, and it's allowed to travel through the air under the influence of gravity. So some examples of this could be cannons shooting off of cliffs, balls rolling off of tables, soccer balls kicked into the air at some angle. It could be a variety of things. So let's get into it. If we were to have an object shot in projectile motion, there's a couple of things that we need to be aware of. First off is that it's basically what we're doing is we're combining motion in two dimensions. So the first is the actual path, which is going to go down like this at this angle, not at this angle, in this arc, right? This is an arced path, and it turns out it actually is a parabola. But what I want you to notice here is the two paths of what it could do. So the first path that it could do, this is if gravity was not a thing. So if gravity didn't exist and we launched this projectile at a constant speed, it would follow the dotted red line. And each of these black dots, equally spaced apart, indicate equal time distance as well, because we know constant velocity means that for the same amount of time, we always go the same displacement. So those are equally spaced out points along that red line if there was no gravity. Now, conversely, if we look over here, this is the path that would happen if there was only gravity and we did not give it an initial velocity. So obviously, it would fall straight down, and we know that it would accelerate and speed up as it does so. We know that gravity is an accelerating force, so it would slowly get faster and faster and faster. So the thing about projectile motion is we have to kind of squish these two paths together. So in the horizontal direction, it wants to move at a constant velocity. In the vertical direction, it wants to accelerate and get faster. So what I want you to notice here is that these line up in time-ish. The diagram could be a little bit better, but hopefully you can see that in general, these line up in time. So what ends up being very interesting about projectile motion is that the object will travel at a constant velocity horizontally while accelerating vertically. So if you were to shoot a gravity-free projectile and this blue line projectile, horizontally, they would go the same distance in the same time. Now, vertically is a different story. So vertically, if we are to look at how far it's moving every second, so the first is right here, right? So within, let's say these are each 1 second intervals. So after the first second, it hasn't moved that much. The second unit of time, it's moved a good deal more. The third unit of time, it's moved even more. And then finally, it's moved a whole heck of a lot. And we know that this should be true because the object is accelerating vertically. So it's going faster and faster and faster, meaning it covers more displacement per unit time every second. So that's generally what we should be getting out of our understanding of what projectile motion is. So here's what we want to think about. We want to think about the net force on the projectile. Why does it not change its motion horizontally? Well, there's only a net force in the vertical direction, gravity. Nothing is affecting it in the horizontal direction. Once the cannonball leaves the cannon, there's no longer any force acting in the horizontal direction, so it's going to stay at a constant speed. So it's going to maintain horizontal velocity, but accelerate in the vertical direction. So for projectile motion, we're going to need to consider the x and y directions of motion independently. And what I mean by that is that what is happening in the x direction has no importance whatsoever to what is happening in the y direction. So what that means is we can set up completely different kinematic equations in the x and y directions. They act separately. And the only thing connecting the two motions is going to be time. Time is the only connecting factor because it's going to take the same time. So it starts at the same time and it lands at the same time. So you don't land horizontally first and then vertically, you just land. So the total time that it takes to launch and land is going to be the same horizontally and vertically. And that ends up being a pretty important factor, actually. So let's start with an example. And this again gives us kind of a good image of what's happening in the vertical direction. So we can see the red, right, it matches vertically the displacement, and it maintains that same length horizontally. Anyways, so let's do this. A ball is launched off a cliff of height 34 meters horizontally with a velocity of 15 meters per second in the x direction. What time will the ball hit the ground, and how far away from the cliff will it be? So let's try to solve this, and so we're gonna need to break these up. We'll do the vertical direction first. Let's do the y direction. So let's list some stuff for the y direction. So Vy0, so the initial velocity in the y direction is going to be 0 meters per second. And that is because we have not given it any initial vertical velocity. We've only given it initial horizontal velocity. What else do we know? We know that Ay is going to be 9.8 meters per second squared. And that's really all we know in the vertical direction. So things that we might want to know are what is the time. We might want to know what the final velocity is. Oh, I'm sorry. We know one more thing. I was mistaken. We know that the I'm going to call it delta y, since we're in the y direction, is going to be that 34 meters, and that's going to be very important. So what we might want to know is we might want to know what the time is, or we might want to know the final velocity. So that's in the y direction. Now in the x direction, let's think about what we have. What do we know? We know that Vx0 is that 15 meters per second. And interestingly, since we know that it's constant, we can also say that Vx, V final, in the horizontal direction is 15 meters per second. And what we want to know is delta x. That's the end goal here. We want to know what time, so this is really what we want to know. And then we want to know where this will hit. So the time is what is going to be the connecting factor here. So whatever we find for time in the vertical direction, we can then apply that to the horizontal direction. So why don't we attempt to do that? In the y direction, what can we use? Well, we have the initial, we have a, and we have delta y. We want to know time. So if we set up, we'll use y's here. Y equals y0 plus vy0 delta t plus 1/2 ay delta t squared. All right, and this is just one of the kinematic equations. We can subtract y0 over, giving us delta y equaling vy0 delta t plus 1/2 ay delta t squared. Vy0 is 0, so that becomes 0 delta t, which of course drops. And then that's plus 1/2 ay delta t squared equals delta y. So what we're left with is delta y equals 1/2 ay delta t squared. And what do we know? We know that ay is 34. 1/2, I'm sorry, delta y is 34, 1/2, ay is 9.8, and delta t squared is left as delta t squared. That's what we want. We want delta t. So if we do 1/2 of 9.8, that gives us 34 equals 4.9 delta t squared. So if we divide by 4.9, we're going to end up with 6.94 equaling delta t squared. And then, of course, we take the square root, and we end up with a delta t of 2.63 seconds. So now we know delta t. All right, so that's what the first piece of information we wanted. What time will the ball hit the ground? So 2.63 seconds later. And then from here, we're going to want to know how far away from the cliff will it be. So how far away from the cliff indicates that we're looking in the horizontal direction, where we know that the velocity is a constant 15 meters per second. So now we know that Vx equals delta x over delta t. So if we multiply by delta t, we get delta x equals v delta t, 2 of which we know. We want delta x. We know 15 times 2.63 seconds, giving us a delta x of 39.45 meters. And that's the other piece of information that we wanted to know. Okay. So what did we do here? Well, we said that these two things are basically mutually exclusive. The vertical acceleration and the vertical velocity has no impact on the horizontal acceleration or the horizontal velocity. But they were connected by time. Like I said, you don't hit the ground vertically first and then horizontally. You hit the ground at the same time. So we were able to find the time and then transfer it over. So we found time in the vertical, transferred it over to the horizontal, and then we were successful, right, in finding the total displacement in the horizontal direction. All right, so what I would like you to do now is have whoever's in here pause the video. I'd like you to try this problem, and then I will go over the solution. A projectile is fired off a cliff at a horizontal velocity of 10 meters per second. If the cliff is 20 meters high, how long will the projectile take to hit the ground, and how far away from the cliff will it land? So go ahead and pause the video, and then we will come back and answer the question. So good luck. All right, I'm assuming you're back. You have paused and resumed. So let's give this a shot, shall we? Let's start by listing our stuff. So we know that in the y direction, the cliff, delta y, is 20 meters. Of course, we know that Vy0 is 0 because we are launching perfectly horizontally. Ay is going to be our 9.8 meters per second squared. And something that we might want to know here is how much time does it take to fall. Then in the x direction, we know that the velocity is 10 meters per second, and we might want to know, or we do want to know, what the displacement is. So we're going to do basically the same process we did before, where we're going to start in the y direction. We'll have y equals y0 plus vy0 delta t plus 1/2 ay delta t squared. And if we subtract y0 from both sides, this becomes delta y equals vy0 delta t plus 1/2 ay delta t squared. And vy0 is 0, so this term goes away. We get delta y equals 1/2 ay delta t squared. Now we can throw some numbers in here. Our delta y is 20. equaling 1/2 AY 9.8 delta t squared. So we'll finish our calculation. 1/2 of 9.8 is 4.9 times delta t squared, divide by 4.9. So we get 20 divided by 4.9 equaling 4.08. That equals delta t squared. So we square root both sides. We get a delta t of the answer 2.02 seconds. And that is the time. So that's from the vertical. We can then transfer this over to the horizontal, where we know that Vx equals delta x over delta t. Our Vx is our 10 meters per second, equaling delta x over 2.02 seconds. So we times 2.02, and we get 20.2 meters is our displacement. All right, so we have successfully succeeded. Hooray. All right, so hopefully you got that. If not, I hope you followed along and were able to understand what was going on here. Do feel free to contact me with questions, concerns, comments, etc. All right, now, this is a projectile at an angle problem. And I don't know that I want to actually have you do this. So give me 2 seconds. I don't want to stop the video, but I'm going to check your work here. Let's see what I'm going to have you do. All right, so what I think I'll have you do in lieu of doing some stuff at angles, and now it is doable. You just have to use some trig functions to determine what's going to happen vertically and horizontally. But I'm going to leave that alone. We might do that when we hit review on this, but I want to wrap this up right now. So we won't do this right now. What I'm going to give you is, so you'll have a couple of things that you're going to need to accomplish this week. This shop week. So one of them is a projectile motion problem set. However, you're not going to do the ones that have the angles. I printed them, but you're not going to do the ones that are shot up at an angle because I'm not going to go over that right now. So what are you going to do? You're going to do the projectile motion problem set. I think it's just numbers 1 and 2, so just horizontally launched projectiles. You're going to do the constant acceleration problem set. So that's where you're going to use the kinematic equations and come up with, you're going to calculate various quantities based on various other quantities. So for the constant acceleration problem set, you're not told what equation to use. It's going to be up to you to determine what you need to use and then successfully use it. You're also going to do the kinematics AP test questions, which you will get, multiple choice and 1 open response question. You'll be able to answer all of them. I am very certain. Then finally, since we are, and I hate to do this to you, but you may have gotten lulled into a false sense of security early this year because I was still trying to find my footing. But you're now going to do guided notes to prepare us for the next unit. So what you're going to do is you're going to get a packet that has guided notes. I have uploaded an assignment to Teams. That is your guided notes. It has the reading. So you're going to read a section of the book, the OpenStax physics textbook that I've already sectioned out for you. It's attached to the assignment. And you're going to fill out the guided notes. You're going to write down new vocabulary, new variables, and new formulas. And then you're going to do 2 practice problems the page number and question number, which I have given. And I've also indicated what example problem from the reading you should refer to in order to solve the problem effectively. So what are you going to do? You're going to do the projectile motion homework 1 and 2. You're going to do the constant acceleration problem set. You're going to do the kinematics AP test questions, and you're going to do the guided notes. And you can do those in any order. They're all going to be due on the Sunday before our next academic week. All right. So thanks for sticking with me. I'm sorry I can't be here today, but it is what it is, and I will see you later.